Today's speaker is a very distinguished speaker. We are very honored to host him as is Professor Max Welling. He's a research chair at the University of Amsterdam and he's full professor there. And he directs the research group, AM Lab, and he's a distinguished scientist at MSR. And is also fellow at the famous institute, SciFar. Everybody in machine learning knows that institute. And he's also a founding board member for Alice. And he was the VP for Qualcomm Technologies. And he was a professor at UC Irvine, postdoc at Toronto and UCL. And he was also editor, associate editor-in-chief for the most well-known prestigious IEEE PAMI from 2011 through 2015. And he was program and general chair of NeurIPS in 2013 and 14 respectively. And he received numerous awards, including ECCV Condoring Prize in 2010. And just this year, the prestigious Test of Time Award at ICML 2021. And he directs co-directs two labs, Qualcomm UVA Deep Learning Lab and Bosch UVA Deep Learning Lab. So without further ado, let us welcome Professor Max Welling.
Thank you very much for the kind introduction. So I hope everybody can hear me. See if I can.
For the audience, you can always ask questions either on chat board or you can turn on your audio. And we are also simulcasting through the YouTube channel, although there's about 10 seconds delay. So please keep that in mind. Thank you.
Yes, I'm happy to take questions in the middle, as we have 15 minutes for the talk, actually an hour total. So we should be able to have some discussion. Yeah, I'm gonna talk a little bit about deep learning and the way it interacts with science. I think this field is going to be increasingly important. So we've seen a lot of applications of deep learning to engineering, but I think now the age of deep learning for science is starting, and we're seeing a lot of really exciting applications of that. So I work at Microsoft since September this year, so very recent. And in Amsterdam, we're going to start a research lab precisely on this topic, which is using machine learning and deep learning to improve our understanding of molecules. And I'm also research chair at the University of Amsterdam. So there's a lot of people that I've worked with over the years for these to get to these ideas. Too many to really mention. There's a couple of interesting reads maybe. So the thesis of Taco Cohen is interesting. It introduces equivariance in deep learning. Maurice Weiler has recently written a beautiful paper on coordinate-independent convolutional networks, beautifully all illustrated. You'll see some illustrations in this work. And then Mark Finzi has written a very nice paper on basically how to generate equivariant kernels for your deep learning architecture. And so you can read that in this paper, a practical method for constructing equivariant multilayer perceptrons. So I'll be talking about symmetries and equivariance. I'll talk about graph neural nets, equivariance for molecules, or equivariant GNNs for molecules, which seems to be the most interesting application right now for this particular scientific application. I'll talk about PDEs, which is something much more recent that we've been working on, other groups have been working on, using GNNs to solve PDEs. I think there's a huge amount of work that can still be done there. And I'll conclude. And here's one of these pictures that I alluded to, which is out of the paper by Maurice Weiler. So this illustrates the fact that if you want to do deep learning on a manifold, in this case, a sphere, you run into a particular problem I'll get into a little bit. And you'll need basically to understand how different coordinate frames describe a signal on a manifold, and how to then transform one of these reference frames to another one. Once you understand that, you can actually do consistent deep learning on manifolds. Okay, and the computer doesn't advance, which is not good. There we go. So equivariance and symmetries are deeply related, and of course in physics, equivariance and symmetries have played an incredibly important role. Let's look at the theory of electromagnetism, which was developed in the turn of the last century, the previous century, between 1800 and 1900, where people first had two theories, one about electricity and one about magnetism, and they thought there were two different phenomena. Now, it turns out that if you sort of consider two different observers, the reference frames that different observers use, if they have relative constant speed relative to each other, then it turns out that electricity can turn into magnetism, and magnetism can turn into electricity. And there's a unified theory, which is Maxwell's theory, which describes all of that in one set of beautiful equations. And it's the same set for every observer in every reference frame. So we call this covariant equations, and basically you will understand you will understand nature much deeper if you really take into account, the different transformations between different observers and how they see the world. The same thing happened also. So basically the theory of, electromagnetism is based on special relativity, the Lorentz transformation, which is, transforming one observer into another observer which has constant speed. If you also think about accelerated reference frames, where one observer is accelerated relative to another reference frame, you suddenly introduce forces, and in particular, the gravitational forces, which turn out to be equivalent to acceleration. So in other words, Einstein realized that if you are in a an elevator, let's say, or some kind of box, and you do some experiment with a ball falling on the ground due to gravity, that experiment is exactly the same, and indistinguishable from the result that you would have gotten if you, would be in a rocket which would accelerate outward. Of course, there's a slight radial issue here that, it's not exactly the same, but the two phenomenon are equated in general relativity, which then, gives you a whole new theory. Okay, so even the standard model of physics, which has all the particles in it, the leptons and the bosons, and the quarks, all of that is also organized using symmetry transformation. So they're, different, let's say, sides of the same coin. You can transform them into each other using group theory and group transformations. Now, in deep learning, we also have symmetries, but perhaps a bit different. But this was the start of our thinking when Taco Cohen joined MLab. So the idea is that if you look at certain images, in particular in sort of medical imaging, then if you rotate the image, the class label of that object doesn't change. So at the level of objects, the orientation or the location of the object doesn't change what it is. And that you can think of as a symmetry transformation. So that sort of creates some kind of invariance. And then we argued that, well, maybe there's a more general concept which we could call equivariance, which is that if you transform the input, you would require certain transformation properties of your hidden representations. And then in the end, things would become, at the class label, things should become invariant. At the level of the representations, things should transform in predictable ways. You can think of, let's say, a segmentation mask. If you would segment this image, you would want that the segmentation mask would rotate with the input image, and that's what we call equivariance. So here's the sort of more formal definition of equivariance, again with a beautiful picture from Maurice Weiler. So let's say here we have some object. In this case, it's an egg, and we have a signal on this object. But typically, we think of this as an image, right? So it's a flat Euclidean space. So let's be a little bit more general and think of general manifolds. And we have some signal on that manifold, like in this case, a gecko. What we would like is some sort of operation which filters that or analyzes this, right? So here we have an edge filter, and you sort of can see that it's sort of whatever it does. It segments out the thing, and then it has some asymmetry where it likes these edges on this side more than edges on the other side. So that's some filter that you can learn. And equivariance basically says that if we transform under some kind of symmetry group, which is in this case rotating over this axis, then we would like that if we first transform and then filter, or first filter and then transform, we get the same result. And although if you look at it, it feels obvious, and it feels like, well, if you take any neural network, this would happen, but it's not, right? So because when you enter numbers in a computer, you really have to make choices. You have to make choices about how to order your pixels, and what you choose to be north and east and west and south and all these things. So when you make these choices, suddenly if you rotate the image and you don't tell me what these choices are, then you'll get different outputs. So you will have to have a theory which will make sure that if you rotate the input image, whatever, so your architecture, whatever it is, should have nice properties under these transformations of these input images. So there's a couple of advantages. The first thing is that when you do that, you find that the structure that you will create internally in these hidden layers is going to be much more structured than if you don't do it. So in other words, we know already that if you look at a CNN relative to an MLP, in a CNN, you get these sort of feature maps, right? So these, we call them channels. And that's already some kind of structure that you're imposing on your hidden layers. Now, if you also use rotational symmetries, then this further decomposes into sort of capsules where there's a number of these feature maps which have some internal transformation properties, which you will come to in a moment. This structure, this idea does work on manifolds as illustrated in this picture. And the advantages are that the more symmetry you will impose on your neural network, the more efficient, data efficient your neural network will be, because you're going to share parameters between certain filters. This already happened, of course, for CNNs, right? Instead of having different parameters for every pixel, you now have, one filter, and you apply the same filter everywhere in the image. Now, if you go use more symmetries, then in fact, you'll find that the same happens for rotations as well. The other thing which is happening is a property which also seems to be happening in the brain, which is called disentangling of pose and presence. So in the brain, we do represent the presence of an object invariantly, like doesn't matter how it's present, but we seem to encode for the presence of an object as well as its pose separately. And this happens beautifully when you think about symmetry. So you'll get these capsules, and I'll talk more about it, but you'll get these capsules, and inside a capsule you encode for pose, where the total activation of your capsule will encode for the presence of the object. And the final thing is that when you have this type of property on your latent representations, what's happening is that the structure will help you will also help the next layer to discover sort of new structure, right? Because the layers of a neural network will have to sort of find increasingly abstract structures in the input, like edges, and then edges of edges, which are sort of corners, and then you build up to more and more abstract things. And so having these properties on your hidden layers makes it easier for the next layer to discover these patterns. So sometimes you can sort of argue that one property or one way to understand equivariance is to say that abstractions, as you go through the layers of your neural network, preserve symmetries. So if you have, like, say, images of faces, right, each on an orbit, and then the orbit is to actually change the orientation, which is your symmetry operation. Then if I would now abstract to an abstract face, and I would map both of these on the same point here, then it also turns out that these rotated copies after your, your symmetry transformation will also map to the same rotated abstraction of a face. And that's, of course, very nice, structure to preserve in the layers of your neural network. So we say that abstracting or going through the layers of a neural network preserve these symmetries. So in a little bit more detail, what equivariance is. So if I have a function that maps from x to y, this would be your convolution. And I have some symmetry transformations, phi, one in the x domain, the input domain, which is this one, let's say, translation, and one in the y domain, which is in the filter domain and the latent variable domain or the hidden layer domain. Then we would like that there is a commutation relation between these things. So or a closing of a diagram. So we say, if we first translate and then filter, we want this to be the same as first filtering and then translating. And that's expressed in this particular formula. Now the function f is going to be the same, but the operation that we apply is different, perhaps, if we apply it to the argument of the function than if we apply it to the output of the function, because the function doesn't necessarily map from, one space to the same space. It could map from one space to a different space. And in fact, in this example, I'll show that that's exactly how things work. So here I have an input image, which is Mona Lisa. We will do we will define two capsules. The first capsule is an eye capsule, and the second capsule is a mouth capsule. And this is the capsule is defined by basically 3 oriented filters of the eye and 3 oriented filters of a mouth. Now, in this particular orientation of the image, it's these filters which will fire, the mouth here and the eyes here, and these will not do anything because they have the wrong orientation. But if I rotate the image and I will again do my detections, then these will not fire, but then these will fire. And so what we see is that we have an internal rotation of the detections, but also we have sort of a shift through this capsule space. What this means is that the fact that this part of my capsules fire means that I've encoded the pose as upright, where here, this part of my capsules fire, which means that I can also read out the pose of my image, which is 90 degrees, right? And so we have this more complicated operation here in this part of the space. Here is the symmetry transformation is just a rotation, but here it's a rotation and a shift in this capsule dimension. Now, you could think that normal CNNs are perhaps already equivariant. Turns out that they're not, and you can easily see it. So there's a couple of illustrations that are made here, but this one is a very old one, which you can find on Jan LeCun's webpage, where you can see under translations, all your feature maps beautifully translate. But if you start rotating things, then in fact they don't, right? They change as they rotate. And here you can see something similar. So you have an input image, and you have sort of a normal CNN, and this is a model by Daniel Worrell called Harmonic Network, and he also made these illustrations. You can see that if you look at the filtered images, if you keep them sort of stabilized, then for the normal CNN, as you rotate, these filter activations, dramatically change around. Where if you do something that's invariant, then they will not change around. Now, in fact, you can define these. You have two types of, say, equivariant neural networks. One is based on these discretized sort of discretized versions of your symmetry group, like the 90 degrees rotations that I just showed. But you can also build what's called steerable CNNs. And then instead of discretizing your group, you sort of separating it in a different way. You're basically looking at the low frequencies, and then so you're cutting off at frequencies. So there's the low frequencies you take into account, and then at some point you get to higher and higher frequencies, like in a Fourier decomposition or harmonic analysis. And then the highest frequencies you typically throw away, because you would need an infinite amount of representation power if you wanted to take all of them into account. But what you get is you get something then that actually transforms under any rotation, so the full continuous group. And so here you can see this is the input image. These are the stabilized views. So basically you transform, but then you have a camera that sort of moves around with the object, and then you just show what the actual, what the camera shows. So here you get the scalar layer, so a layer where the output is just scalars, and you see that they beautifully transform around with the object. And here's a vector layer. So this is feature vectors that live in a vector space. And you have also nice, transformations. But in this case, of course, they're in some funny vector representation. Okay, so again, as said, here's this paper that you could look up, where there's an algorithm, efficient algorithm, that provides for you the equivariant kernels. The only thing that you would have to do is give the algorithm, the representations of the input layer and the output layer, or no, sorry, the representations of the first layer and the next layer. And you would have to give the generators of the group, and that can be both, for a continuous group, which would be the algebra generators, or it could be for a discrete group, which will be the generators of the discrete group. And it's a pretty powerful idea, because there's these groups that have a huge number of elements, almost 10 to the 20 elements. But then since there's only 6 generators, you can still come up with the full equivariant basis for that neural network using that code. Now, convolutions, we are used to doing convolutions in sort of flat space, right? And in flat space, we have some kernel. And then in order to define our convolution, we have to move that kernel to some other point in space. And we kind of used to the idea that it doesn't matter which path we take, we just move it there. And then it's defined, it's uniquely defined how to do that. Because it doesn't depend on the path, so you don't have to specify the path, right? And so you can just shift your convolutional kernel around to everywhere, and then you can sort of do your convolution everywhere. Now, in a curved space, this is different, and you can see it here nicely on a cube. So if I move something over the cube here with what we be your most intuitive definition of sort of transporting your kernel, or if I move it here and then here, right? Locally, you would think every time you do that, it's perfectly parallel. But then when you get together again, now it's rotated, right? And so one way to view that is to sort of cut open the cube, and you say, well, in one way I'll move this way, but in another way I'll move this way. And if I move this way, we have this weird identification problem that, if I move in here, I come out rotated this way, because there's an angle deficit here, so the angle is missing. And so that's why on a curved manifold, the path actually determines how your sort of kernel is defined when you transport it to another location. And this gives issues if you try to define sort of say convolutions on a manifold. Now, the way to resolve it is to acknowledge that there is no global reference frame. So basically, like in general relativity, which is the theory of gravity, people also acknowledge that there is not one global reference frame for every observer in that spacetime. So the best you can do is to assign local reference frames to everybody. So everybody uses their own way of measuring the world, chooses their own coordinates if you want. And then when you move something, you just have some definition of how to do that. So the most natural one is called parallel transport. And then you basically have to say, well, I move it this way, but then this person has a different reference frame. So then I have to map it to this different reference frame. And when you take into account the different reference frames and how they transform into each other, and you define your convolution in such a way that it doesn't care about the reference frame. So it is this, in other words, it's a reference frame independent definition for how you do your convolution. Then you can change your, your coordinates in any way you like, and you'll still have a consistent way of describing the signal on your manifold and the convolved signal in your manifold. So that's the idea of a gauge CNN, and you'll have to read the paper to get more, details clearly on how that works. Now there's a practical implementation of this, which we call mesh CNN. In a mesh CNN, we divide the space up into sort of a grid, a mesh, right? And then we just treat it as if, almost as if it were a graph neural net, right? So in a graph neural net, you send messages from neighboring nodes to your central node. And typically, when a graph neural net, you don't care precisely where these points are, because it's just a graph. So I could move this guy here and it wouldn't have to matter. And in a graph neural net, that restricts the way you can send these messages. But if this represents an actual geometry, then you do want this to be different from this. And so we need to make some choices, some changes to the graph neural network to make that happen. And in a way, the way this works is, so here's the two equations. So this is a graph neural net. So graph neural net takes the signal for the neighbors, the feature vectors for the neighbors, pushes it through some weight vector, a kernel, but the kernel has to be the same for every neighbor. And then you sum them up, and you can also send a message to yourself, which is different from the one you get from your neighbors. What we do for a mesh CNN, which is, so the first thing we want to do is we want to first so we acknowledge that everybody has their own reference frame, right? And there's a transformation between these reference frames. So we first map it okay, let's say we are in this space here. We first map it to our particular gauge, which is a particular reference frame. We then parallel transport it, and then we map it back to the reference frame of the other person. So geometrically, this looks like this. So you have some reference frame. You can think of this as some kind of tangent space to this point, which you can sort of define as balancing on this point here. We have some vector in that space. And what we need to do is we need to first, move this in the reference frame of the point we want to go to, which is we have to sort of reorient our tangent space, and then move the vector to here. And once we are here, we have to then transform to the reference frame defined by this person. So that's another transformation. And then we can do our convolution. And so it looks a lot like a graph neural net, but it has this additional sort of transporter here, which both does the parallel transport and the transformation between the different reference frames. Otherwise, it's similar, but the most important thing is that now this thing depends on the angles. It's not the same kernel for every neighbor, but it's a different kernel depending on the angle and potentially also the distance from between the 2 points. So yeah, so I already talked about graph neural nets a little bit. So a graph neural network is sort of a simpler version, if you want, than this mesh CNN. And the point is that in this case, since there is no geometrical structure underlying the whole thing, you have to send the same messages from each one of your neighbors. Now, there's more general descriptions of this, which is called message passing graph neural net, which I will be using, which is basically you look at the feature vectors of your two neighbors, hi and hj. There's some other information perhaps living on an edge. You take some kind of function, could be a neural network, that takes in this information to produce a message for going I to j. You then collect all the messages from your neighbors, and then you go through another step of where you take this message, this aggregated message, plus the feature vector living on that particular node, and you do another neural network, let's say update or nonlinearity, to get your new feature vector at the next layer on that node. So this is the more general one, but note that it's still the same as every neighbor still uses the same formulation, phi I, to compute their message. And that has to do with the fact that it's a graph and not a mesh. So why all this is interesting? Well, because we want to apply these to things like molecules, right? So a molecule is a bunch of atoms like these, and there's a whole bunch of electrons flying around. Just you can think of them as some kind of cloud. And there's forces on these atoms. So if you want to, so if you think about the alpha fold um, sort of algorithm, you can think of it as applying computing forces on each one of these atoms, and then moving these atoms according to these forces, right? And so there is sort of a Newtonian dynamics on this system, which is the time derivative of these locates, sort of the way that they change their position is given by the velocity, and the change in the velocity is given by the forces. The forces are the gradients of some kind of potential, which this is often called a force field. And the force field has to be computed using quantum mechanics, which is very, very expensive. Now, molecules are really important. And, you know, there is most things around us are actually made of molecules. Of course, you know, if you go deeper, um, you will get to quarks and stuff like that, or, you know, you can create plasmas, which are basically, you know, where the molecules have been destroyed. And then there is some forces like gravity and nuclear forces and light, but everything else is basically that you see around you is made of molecules. And so it determines a lot of properties of the materials that we're using. So for instance, it's useful for drug discovery. If we understand precisely how two molecules bind, let's say a protein to some kind of drug, then if we can sort of search the space of molecules that binds to a particular protein to suppress the disease. If we understand, you know, the photovoltaics is the field where we take light and turn light into electricity and energy, and also molecules determine basically the properties of these solar cells. 20% of all the energy that we lose in the world is because of friction. So it's worth to come up with new compounds, new molecules that reduce friction between sort of two materials, called lubricants. Now, catalysts are extremely important, for instance, for things like fuel cells and batteries, and you know, hydrogen production, fertilizer production, which is called nitrogen fixation. So all of these things could go much more efficient, could work much more efficient if you would have better catalysts. So the search for better catalysts is another sort of interesting application of this field. And finally, of course, we would like to understand the entire workings of the cell, which is far more complicated and would use hundreds of millions of molecules. Now, what are the key challenges in this field? The key challenges is to do more accurate simulations of molecules. And as I said, you need quantum mechanics to understand quantum mechanics or approximate the quantum mechanics in order to do that. We need faster simulations because molecules change at the sort of time scale of femtoseconds, which is a millions of a billionth of a second. And so we would have to accelerate this, I don't know, 8, 9, 10 orders of magnitude. And finally, we want to look at much larger scale simulation. So we need to be able to coarse grain or find ways to coarse grain you know, molecules into sort of supermolecules or cells or something like that, and have these different, you know, scales interact with each other. Okay, so I'll skip this. So so what I want to introduce here is a equivariant graph neural network, which we designed with these people here, Victor and Emil. We designed it to be both a graph neural network to describe a molecule, as well as have this equivariance property, because we know that if we take a molecule and we rotate it, or if we translate it, it will still be the same molecule. It will have the same properties. So if we have, let's say, a molecule here, it has some scalar properties, like these things here, and it also has some vectorial properties, which could be like there's forces or velocities or something like this, as well as their positions. Now, if you have some operation that transform that, like in a graph neural network, then of course our scalar properties all change and our vector properties all change. And in fact, the whole graph layout changes. Now, if we say we first rotate, right? So you can see that x4 rotated all the way to x4 here. So our the scalar properties remain invariant, and our vector properties rotate accordingly with the rotation of the transformation. Then if we first do the rotation and then do the mapping, the neural network mapping, it should be the same as first the mapping and then the rotation. That's what we would like from a model that describes molecules. So in more detail, so we have a state. It has a bunch of features, h, positions, x, and velocities or forces, v. So these all will change as we go through the layers of a neural net. We have some fixed features on nodes and edges, like maybe types or something like this. Or yeah. And then there is invariance, things that don't change under the symmetry transformation, which are h and xi minus xj. Right. So these will change under the transformation of the neural net, but they don't change under the symmetry transformation. So we then define our message updates, like very similar to what I described before for message updates. So we first compute the message on an edge, which now takes into account again these invariant features on both sides of the edge. It takes in the distance between the positions of the atoms, that's invariant too, and some other information. And we push this through a neural network to get ourselves M, which is now an invariant message. This thing doesn't change if I rotate because all the arguments are invariant. And then I do a very simple update, as a compute a velocity update, which is the old velocity times some function times the distance vector times some other invariant function. And since these are scalars and these are vectors, the whole thing is still a vector. I can then update my position using this new velocity. Again, only vectors of the same kind, so this will still be a vector. I'll aggregate the messages, which is a scalar, and I'll do my other neural network update to get my new scalar quantity h. So this is a nice update, which we are now guaranteed that the h's will remain invariant and the x's and the v's will remain type 1 vectors. Now we extended this in this paper, which actually came earlier, but it's also slower. So there's advantages and disadvantages between these things. It's called the SE3 Transformer. Now, a transformer again sends messages in this case. So typically, a transformer exchanges messages between all nodes or all entries. So we had sort of a finite radius in which we would send messages. And the messages here in this case have a particular form. There are these sort of query key types of things. We compute a query queue, we compute a key, which are defined as with some matrices W, which are a function of the difference vector xi minus xj between the two exchanging vectors. And then there is some somewhat complicated thing going on how to make sure that this W function of x is actually a proper tensor object. So if I multiply this with f, it will actually give you a nice vector coming out at the other side again. Now this is not just 3 vectors. We can have now much higher order representations of the rotation group. And in order to do that, we will need these Clebsch-Gordon coefficients and spherical harmonics and all these things. It's a bit detailed and complicated. You can read it in the paper. In the end, we'll compute attention weights using our queries and our keys. The attention weights are invariants. They don't change under rotations. The things that we are exchanging, the V's, are vectors, higher order representations of the rotation group. And then we sort of accumulate all the different messages, but now proportional to their weight vector alpha. So again, invariant, equivariant vector, the whole thing is again an equivariant vector. We yet again generalize this, and again it gets more complicated, to have more general functions than what the transformer used. So what's interesting is that people think of the transformer as a generalization of things, but I think of the transformer as a special case of a GNN. It's a very particular type of messages with queries and keys that are being exchanged, but it falls perfectly into the GNN framework. But you can do more general exchanges of messages by not, instead of using queries and keys like here, you can use general MLPs, equivariant MLPs, multi-layer perceptrons. But if you make these equivariant MLPs, and you otherwise the construction is very similar, right? You take your invariants as input, or in this case, you take your feature vectors, which are in this case vectors, and your distance vectors as input. You push them through an equivariant MLP, then you know that what comes out on the other side is going to also be a proper representation of the rotation group. So it's some kind of object which we know how to transform under rotations. And so we sort of, we again it uses spherical harmonics, and we will get a nice sort of equivariance again. So we start with these representations, we rotate or we transform, and rotating and transforming, or transforming and rotating should come out to be the same. So here you sort of see this thing in action. These funny blobs here are one way to represent functions on spheres. So we basically have some function on a sphere using spherical harmonics, and you can see as we move through the layers of the neural network, these functions on these spheres, change because we are exchanging messages on the nodes of this graph. The whole thing is guaranteed to, if I rotate this object around, it will just give you exactly the same picture, but now rotated, and that's exactly what we want. Okay, so the next thing I want to talk about has to do with, so the previous models were mostly used for, take an input and predict properties like a normal neural network, supervised learning. You can also use equivariance for unsupervised learning, and in particular when you do flows. So flow is basically a invertible neural network that takes you from some standard simple distribution like a Gaussian, and you sort of morph it by steps of the neural network into a much more complicated distribution. The whole thing is invertible, and the nice thing about invertibility is that you can just write down analytically what the actual log likelihood is and just do gradient descent on that log likelihood. You don't have to do complicated sort of approximate inference procedures like you would have to do for a VAE, for instance. And so we use that to basically build an equivariant normalizing flow for molecules. So the idea would be you would start with some randomly generated molecules of sort of random types in random positions, and then you would flow these things according to one of these flow ideas into a viable molecule that would make sense, that there could have been a real molecule in the real world, right? And so a little bit more detail on that is you would have to do a couple of things. You first have to map everything into a continuous space, because if you don't do that, you're stuck with some discrete things and you cannot flow over discrete things very conveniently. So that's a process called dequantization, which basically means that you sort of distribute the world into bins. The center of the bin is your discrete state. The value at the center of the bin is your discrete state, but then you sort of diffuse that over the entire bin. So that gives you some full distribution in continuous space. Then we would do one of these flows. It's called a continuous flow based on an ODE. There's quite a lot of details, but maybe let's skip that. So it's not a discrete number of steps, but it's more like a continuous integration where this is the Jacobian. Everything gets then mapped to a continuous space, a simple distribution on a continuous space, plus some distribution which has to do with the number of atoms that I need to generate. And then once we can train this flow, we can also sort of generate or assemble, let's say, our molecules. So here you can see it. So when we rotate it, it's the same probability that we would have generated, and this is the inverse flow, disassembling the atom into something, right? And then now here we go backward again. We assemble it into a nice molecule using this flow. Okay, the last topic I'm going to talk about is applying GNNs to solving PDEs. Now, PDEs, clearly partial differential equations, clearly are basically the workhorse of all of science. Basically, most people in science just write down their models into partial differential equations of some sort. It's a very general, equation. You have some field, U, defined over X space. It's a vector field. And you take the derivative, time derivative of that. So you study how that changes at a particular position x. And that's given by some function. Could depend on t explicitly, can be non-homogeneous, so it can depend on x. It certainly depends on u, and then it depends on the spatial derivatives of u. That's very general. There has to be some initial condition, which is the value of u you start with at time 0, the field of every position x, and some boundary conditions of what happens when you sort of reach the boundary of your domain. Now there's a much simpler version which we studied, which is this sort of conservation PDE, is a PDE which has a conserved quantity, which can be written like this. And if you are familiar with it, this is very much like a sort of a flux equation. And it basically says that, if you take any arbitrary volume in space, you would have to use this kind of Gauss, equation, which says that the divergence, if you integrate over space, can be expressed as a surface integral. And it basically says that the change of stuff in any volume is equal to the stuff that flows in minus the stuff that flows out. So in other words, you cannot create or destroy things inside any volume, which means that the amount of stuff is conserved. So one equation for that is, for instance, the Burger's equations that we will study. Now, the models that we studied to solve this are neural autoregressive solvers, basically of the kind where basically you try to fit a model, as you would expect, that takes your solution at time t, specifies some change in time, and it will map it to the solution at time t plus delta t. We have to write down some loss function, which is also what you would expect, which is the difference between, let's say, ground truth, which could be given by a high, very expensive solver, numerical solver, and your prediction of that new time step. And you would have to, sample these k values and these u values from some distribution, which we do here. So you would have to take some expectation of that. Basically, you generate solutions with a high precision solver, and you would try to predict using your prediction model. There's some tricks in order to make this work faster. One is temporal bundling, which means that you don't predict one time slot at a time, but you would predict blocks of time at one go. And the model that we use is a graph neural net. So it goes as follows. You have some input sequence u in the past at a particular point I. You push that through an MLP to get yourself some feature representation of that point I at that time t. And that will give you this. Then you'll go through a graph neural network, as I explained it in the past, which is just sending messages between the nodes. In this case, the messages are made of, they take as input the differences between the feature vectors, the differences between the values u, the entire feature vectors u in the past, differences in space, the actual parameters of the PDE. All that goes in. There's these neural network updates. Something comes out. And again, a vector, you would have to do some temporal convolving of that signal over that signal to get the final output. But then you can feed that back into here again, right? So then the output of that is the new values of u. They can go back into here, and you pass through this thing multiple times, and that's where you integrate forward.
Can I ask you a quick question about that? What does a node in that graph represent? What does that mean?
Yeah, it's sort of a node in space. So you can see here the I and the JXI is sort of an integration node in your space. So you sort of mesh up your space. You're putting nodes in that space where you do your computations. And so like a
spatial location.
Sorry?
Spatial location. Does that?
Yeah, spatial location. Yeah. Okay. And you can choose your integration mesh. You could even optimize over your integration mesh. You can even backpropagate over your integration mesh. But you want to receive information from your neighbors. right? Because you have these derivatives here, so you need to be looking at your neighbors in order to solve this. That's the idea of a PDE. So this way you integrate information from your neighbors.
How much speed up can you get compared to like conventional numerical, like algorithm, numerical?
Yeah, so it's the
Yeah,
speedups are in the paper, but it's orders of magnitude. So depending also in the integration grid, right? So if you do a very fine integration grid, the speedup is less. But if you take a sort of a less fine integration grid, coarse integration grid, you can speed up a lot. So this is I would have to go to the paper to really know, but it's orders of magnitude faster.
I see. Can it be like applied to quantum mechanics where you represent a wave function, maybe a
Yeah,
Schrödinger equation, something like that?
yeah. So clearly this is my interest, but the real issue is the dimensionality, right? So here we are. This example here is in one dimension. Then you can look at things like Navier-Stokes, like this, in 2 dimensions or 3 dimensions. But if you do Schrödinger equation with, let's say, I don't know, 5 electrons, right? So you have 15 dimensions already, and 5 electrons are nothing, right? It's this very small system. So the scaling with dimensionality is the real challenge here, in my opinion.
Mhm. So there's still a curse of dimensionality here.
Yeah, you don't overcome, yeah, because the integration grid has to live in this dimensional, in this high dimensional space, right? And so I think you would have to do things like, I think we need to define solvers for 3 dimensions, and then make sure that whatever we do in quantum mechanics, we can first map it approximately to these 3 dimensions. Like we can look at charge densities or something like this, and then solve equations there. I think that's manageable, but it's not going to be manageable in 3 times n dimensions, where n is the number of electrons.
I see.
I think that's pretty
I, I,
hopeless.
I heard that there are a lot of open problems, especially in fluid mechanics, where people use like Navier-Stokes
Yeah,
equation. Do you
that,
think this has a potential to maybe open up a new avenue in that research area?
yeah, I think so. So this is Navier-Stokes. So here the top line is ground truth, and the bottom line is basically the neural network approximation of the solver. So certainly, I think Navier-Stokes in 2 or 3 dimensions is definitely within reach. So what's kind of nice is that what you see is that something that looks extremely complicated for a solver, which is these shock waves. So this is a space, and this is the value of u, and the colors is time. And you see that if you start with a smooth solution, the blue one, over time you'll develop these shock waves in Berger's equation, which typically are very hard for numerical solvers. But if you look at, the solutions that the GNN learns, basically reproduces these shock waves quite well. And this is going down in resolution, so the solver gets faster if you go in this direction. So that's hopeful. Now, how well they would be, predicting things like turbulence and stuff like that is of course, I don't know. We have to check it, but those are extremely complicated phenomena, clearly, with very high sensitive, chaotic and high sensitivity to initial conditions. So I don't know precisely how well it would do there, but it's certainly worthwhile trying.
Okay.
So what's also nice, that I wanted to briefly highlight, is that you can in fact, you know, train on, so you can parameterize PDEs by parameters, and then you can train on one set of parameters and then run the solver on a different set of parameters. So it's you can generalize from one PDE to the next PDE to some degree. And the other thing is, this opens up the possibility to actually backpropagate, to actually learn the parameters. So you can just give me some data, and then you can actually try to learn the parameters that describe the PDE, which is also kind of interesting. And something that we didn't do at all here, is to use symmetry. So these PDEs are very rich with symmetries. And of course, you would want to leverage those symmetries when you do these GNNs. So we need equivariant GNNs that are equivariant under this group of symmetries. We haven't gone there, we haven't done that, but that's certainly the next step to see how that, if that helps a lot.
Mhm.
Yeah, so let me conclude. So I think the next decade will see new powerful instruments for chemists and biologists, which are basically these types of simulators and machine learning accelerated simulators that are running, on HPC clusters and cloud systems in order to, do these simulations at much larger scale than we can do now. And the applications of such a system are really very inspiring, because once we understand materials better, we can make new materials and new drugs. So we have applications in sustainability, like carbon capture, hydrogen production, clean fertilizers, biodegradable plastics, and in health, like new vaccines, antibiotics against resistant bacteria, immunotherapy for cancer fights. So basically, there's a lot of beautiful applications once we learn to understand molecules better. And it's also the right time to go into this, which is also how I started my talk, which is there's a couple of things which are really converging in the next decade, I think. So of course, machine learning and compute infrastructure are maturing, and soon perhaps even quantum computing is going to help us accelerate this, but soon meaning 10 years or so. But if quantum computing is realized, one of the first useful applications of quantum computing is, in fact, in simulating quantum mechanics. So there it would be very useful to have it and sort of take care of the quantum mechanical part of these complicated calculations. And then finally, there's also somewhat of a revolution going on in automated high throughput and machine learning driven experimental testing. There's factories being built which completely automatically do experiments and then interact with a intelligent agent to figure out what the next experiment is. So all these things seem to be coming together and open up space for a very beautiful era where we can basically design our own materials and drugs that we wish to build. Thank you very much.
Hey, thanks a lot. Let me just maybe get some questions from the audience. Are there any questions from the audience? You can actually type in yours on the chat board. While we are waiting, maybe I can ask you some questions out of curiosity. You mentioned that graph neural network and also transformers as one of your methodology. What do you prefer in terms of your experience?
Yeah, so I think
what is the better one? Which one is better?
well, a graph neural network is a sort of a more general class of things, right? So for a graph neural network, you would still have to specify your messages, and so one way to specify messages is a transformer. But I don't think that's necessarily the best way for molecules to specify your messages. So I don't see any reason why computing a key in a query and then normalizing and then multiplying and using it. It's basically computing attention weights. That's all it does in
Right.
some way. So I think there's more general ways. The paper that I alluded to after the transformer work is much more general. And in fact, it computes its messages based on general MLPs, equivariant MLPs, which you can then again learn. And so that's much more general than just a sort of an attention weight. It is a much more complicated function that can be learned. So I would say it's one special case that's happened to work very well for language, but I don't think it, I think there's much more general things to be discovered there.
Yes. My other question was like, in the message passing algorithm you described, in a typical case, you actually subtract out the target element from the neighborhood, usually when you do the message passing algorithm in belief propagation, but you didn't subtract out the target element. Is there
I
a
see.
reason for that, or was it just?
Yeah, so in belief propagation, sort of you do probabilistic reasoning, and there you want to make sure that you don't overcount evidence that sort of runs around in circles.
Right.
And one way to do that is to, don't sort of the shortest circle is, you receive something from your neighbor that you then immediately incorporate in sending this message back. So so for probabilities, that clearly gets you poor probabilities, but neural networks are sort of deterministic systems that don't really care much about probabilities. And so we're not trying to do probabilistic inference. Now, I think you can try to remove that message, but you're even sending a message to yourself, right? So that's even worse in that sense. So I think it's you're not really trying to achieve. So first of all, you're learning, right? So in a belief propagation system, you really have a fixed set of parameters and distributions, and you have to do inference over that set. Where here you can just learn these messages to do the right thing in the end, to produce the right thing in the end. So I think there are slightly different objectives. I should say that you can use GNNs to help you do better belief propagation, and there you might exactly want to remove that particular message.
Actually, in typical GNNs, there's you have to take into account that adjacency matrix. How did you incorporate that explicitly or implicitly?
The adjacency matrix, meaning
you go from the graph structure, basically.
Yeah, well, that determines your neighborhood, right? So that determines basically who you are interacting with, so who you will receive messages from, basically.
So it's just defined by the neighbors then.
Yes, exactly. Yeah.
So before we finish, are there any questions? The audience today is a bit shy today. Okay, there's one question on the chat board. Can you see a chat board?
Well, no, I see nothing on my chat.
On the YouTube. Let me just relay that. The question is, can you explain again how you do impose symmetry using serial neural network using MLP, GNN, and CNN? I think it's kind of a general question.
Yeah, so it's of course a very long answer. I think we're already 3 minutes over time actually, but so symmetry goes into the equivariance. So the symmetry determines the structure on your kernel. The kernel has sharing parameters, like you would go from an MLP to a CNN. You would put more structure on your kernels inside in a deep neural network, and that structure is determined by basically the symmetry. And that basically means that if you change something on your input, you get some structured transformations on your hidden layers in your output.
Okay, great. I hope that answers the questions. Are there any other questions from the audience?
Actually, I think I need to move to my next meeting, which is already started.
Okay, sorry about that. Thanks for your valuable time. It was really an honor to listen to your inspiring talk. Hope to see you in person, maybe in future conferences.
Yes, thank you very much for inviting me. Okay.
Thank you.
Bye. Bye-bye.